Hi everyone. In this video, we are going to cover the compound interest. First of all, this is the formula you're going to use. I don't know why this is a simple, supposed to be compound. Okay. This is the formula we are going to use in calculating compound interest account balance. And these are the variables in this formula. So let's take a quick look and then we try to make sense out of this formula. First, Pn is the output of the formula, which represents the total balance after n years. So that's output. And P0 is the initial deposit. If you deposit money, it could be the initial amount of your loan, your debt. Either way, it's called a principal. And 1 is part of the formula, which represents the deposit or the loan amount. And R is the interest rate, is always annual rate. And K is a number that represents how many times the account is compounded per year. For example, if the account is compounded annually, the K is 1 because annual means per year, right? Annually. And if the account is compounded monthly, apparently we do it every month. So how many times we do it per year? It's going to be 12 times, right? So if it is compounded monthly, K will be 12. That's how we determine K. And on the top, in this exponent part, N represents the time, but it has to be in terms of years because this interest rate is in terms of years, annual rate. So N is time in years. And the K is the same K in here. Now you can see this formula actually is very much has same kind of structure in the exponential model. And if I put it in here, if I do a quick comparison, this is our exponential model. Now look at this. This is input, this is output. Here, this n actually is the number of years. It's also input, and this is output. So input is in the exponent, output is here, and it's the initial value. This is the initial value, and this you have a number inside parentheses. You have number inside parentheses. In other words, basic structure is the same. So compound interest is growing exponentially. Okay, now we want to make sense of this formula, why we have such a form for compound interest. Even though this is called a compound interest formula, it doesn't calculate the interest directly. It calculates the total account balance in the end, future value. That means this number has principal, which is this, and interest. Contains both parts. Now let's make sense out of this formula by looking at two examples actually. One is simple interest account, one is a compounding interest account. We want to make sure people understand the fundamental difference between a simple interest account and a compound interest account through these two examples. And based on understanding of the difference between these two types of accounts, we develop that formula. Okay, the first example is that if we deposit $1,000 at 10% annual interest rate for 3 years, we want to find out the total interest amount earned. So apparently, this is a simple interest account. How do we know that? Simple interest account. For any compound interest account, they have to mention how often the account is compounded. They have to mention that. If they don't mention that, you can assume you have a simple interest account like this one. So I'm going to calculate the interest. I equals P times R times T. So that's $1,000 times 10% times time, that's 3 years. So this is $300. This is a very simple calculation. And that's it. That's the whole total amount of interest after 3 years. Now we are going to calculate total amount of interest earned for the compounding account. I don't know if you notice that or not. For these two different types of accounts, we have exactly same numbers. Deposit $1,000 at 10% annual interest rate for 3 years. We need to find total interest earned. Everything is the same. Only difference is these two words. This account is compounded annually. That will make a huge difference in the end. So this way you can tell the different type of account, how they make difference, even though we have exactly the same numbers. Okay, since this one is compounded annually, what does it mean by the way compounded annually? What it means is that they are going to calculate at the end of each year because compounded every year annually. So they are going to calculate how much interest you earn at the end of each year, and then put that interest earned in that year back into the principal, so that for the next year, the principal is increased by a little bit. And they do this year after year, compounded annually, so that each time your principal will increase a little bit going into the next year, so that you earn more interest because your principal increased. So let's do the calculation to see how this compound interest account works. Let's do the year one first. So I'm going to calculate the interest at the end of the first year. So I can use I equal PRT. You may ask why we use the simple interest formula if we have a compound interest account, right? Since this account is compounded annually, as we calculate at the end of that year, that means within that year, there's no compounding. That's why we can still use a simple interest formula at the end of each year. So I equals principal times interest rate times time. It's 1 year at the end of the first year. So we get $100 interest. Now the total amount in the account after the first year equals the original deposit plus the interest earned in the first year. So that's totally $1,100. So this is new balance after the first year, which is also the beginning value for the second year. So this is a new principal for the second year. So let's repeat this calculation for the second year. Year two. So we still calculate the interest at the end of year two, but we have a new principal here at the beginning of year two. We still get 10%. For the second year, we still have 1 year of time. It's not 2 years, it's the second year. So this one will give us $110 interest. And you can see the dollar amount of interest for the second year is $10 higher than that at the end of the first year. So where comes the actual $10 interest? Well, we have this little bit higher principal at the beginning of the second year. So originally we have 1,000 principal. If you use 1,000 times 10%, that'll give you $100 interest, right? But we have extra $100, which is the interest from the previous year. That $100 times 10%, that's how we get this extra $10. In other words, for a compounding account, you have two sources to earn interest. One is from the principal, one is from the interest that you earned from the previous periods. That's why for a compound interest account, for the same initial deposit, same interest rate, same amount of time, you will earn more interest. Because in addition to the principal on which you earn interest, you also earn interest on the interest you earned before. Okay, let's continue. At the end of the year 2, the total account value equals the initial value at the beginning of the year 2 plus interest earned. This will be $1,210. So let's continue to do the calculation for the third year. So year 3, we start with 1,210. We still have 10%. We still have 1 year of time. And this interest amount is 121. So it's getting more and more from 100 to 110 to 121. Now the total account value at the end of the third year, 1,210 plus interest earned, that's $1,331. And our question is find the total interest earned over these 3 years of time, right? So how do we calculate total interest? Total interest? We cannot use I equal PRT anymore because for the 3 years, there's compounding in between. You cannot use a simple interest formula. But how do we do that? We do it from common sense. So currently, after 3 years, we have this total account value. In the beginning, we deposit $1,000. Any extra beyond 1,000 has to be from interest to make sense, right? No matter what's going on in the middle over the 3 years, but the thing is, this money increased from 1,000 to 1,331. It has to come from interest, no other possibility. So total interest is 331. Now you may say there's no big deal here because 3 years of time, this is 331 versus 300. You only get $31 more for 3 years of time. Well, that's not wrong. And it's a small difference in terms of the absolute dollar amount. For that, the reason is your deposit amount is small in the first place, and you only have 3 years of time. And this compound interest account grows exponentially. What that means is that the longer the time, the faster the money grows. It's not that in the beginning it's very fast. In the end, it's going to be very fast. Okay, now as long as you can see the difference between these two accounts, that means you have two sources to earn interest in the compounding account, and you will get more interest for the same set of numbers when you have a compounding interest account. And that's good enough for these two examples. Now we want to derive the formula, which is this. I copied it on this slide also. And by looking at the work we did in the compounding account so that we can derive this formula so that the formula makes sense to you. So let's do that. Year 1, again, I'm not going to redo that calculation. We're going to have this format. So in the year 1, the total account value. The total account value can be written as initial value, which is $1,000, plus interest, right? How do we calculate interest? I equals PRT. So P is 1,000 principal, interest rate is 10%, T is 1. So we don't have to write 1 here because when you multiply by 1, it doesn't make any difference in multiplication by 1. So this is the total account value at the end of the first year. Now I'm going to rewrite this into this format. If you take a look at this, we have 2 terms here. Each term has this 1,000 in it. So this 1,000 is called common factor. Now I'm going to factor out this 1,000 and to help you make sure everybody understands this factoring process. And I'm going to do another one separate from here. Just show you how this factoring being done. So I have a 4 plus 6. 4 can be written as 2 times 2. So each one is a factor of 4 plus 2 times 3, right? You can see both have 2 as a factor, common factor. Factor 2 out, put the result inside the parentheses. How do you do that? Basically, you use each term in the original expression, no matter how long, divide by this common factor and put the result inside the parentheses. 4 divided by 2, that's 2. 6 divided by 2, that's 3. Take a look to see if they're still equal. 4 plus 6, if we do calculation, it will be 10. How about 2 times 5? It's still 10. We just factor the common factor, the value won't change. So I factor this 1000. Now, what do I put inside the parentheses? We go through the same process using each term divided by a common factor and put the result inside. So 1000 divided by 1000, that's 1. This whole thing divided by 1000, imagine that 1000 canceled, you only have 10% left. So that's what we get. And you know this is correct because 10% is 0.1. 1 plus 0.1 is 1.1. 1.1 times 1000, that's 1100. And you know at the end of the first year, it is 1100. We just write it into this format so that we can get this formula. Now let's look at the end of second year, how much we have in the account. So we need to use the initial value in the second year, which is the same as this. This is the beginning value of the second year, plus the interest you earned in the second year. How do we do that? Interest equal to PRT, right? Principal is this. So principal, interest rate is 10%. And time we have 1 year. Again, we don't need to multiply by 1, again, because it doesn't make any difference. If you look at this, we have another common factor. This part, this whole thing is the same. So we factor that out. 1000, 1 plus 10%, this common factor. Now second parenthesis, using each term divided by this and put the result inside. This divided by itself is 1. This whole thing divided by this, you get 10% left. Now take a look. We have 2 parentheses which are exactly the same. This is like something multiplied by itself. So how do we write that? Something multiplied by itself is called a square, right? So this one can be written as 1000 times 1 plus 10% squared. Squared. We get something in here. Now let's do year 3. Year 3 total account value. We start with the principal, which is from last year. So 1000 times 1 plus 10% squared. This is the beginning value plus the interest. Interest equal to beginning value times 10% times t, right? Beginning value times 10% times t, 1 year. Again, we don't need to multiply by 1. Now this time we have this whole thing as common factor. Factor that out. 1 plus, let's write it in here. Factor this out. 1 plus 10% square, right? This common factor. And then every term divided by this common factor, we get 1. This whole thing divided by that, we get another 10%. You see, this time we have 3 parentheses. Without anything here, this is 1. Total is 3 now. 1 plus 10% to the power of 3. Now we don't need to continue because you already see the pattern here. You always have 1000. You always have 1000. For year 1, you have 1000 outside the parentheses. Year 2, you have 1000. Year 3, you have 1000. But in terms of parentheses, you always have this 1 plus 10%, 1 plus 10%, 1 plus 10%. Only thing different is this. If here is 1, you got 1 here. If there's nothing, it means 1. If you have 2, you have 2 here. If you have 3, you have 3 here. They're always the same. So what if we have a number that is not 1, 2, 3? Any other number, they're still the same. If this is 10, after 10 years, that's going to be 10, that's going to be 10. Is that right? So it's just a different number, but always the same. So I can rewrite this into this, like something like this. Yn equals year n will be 1000, 1 plus 10% to the power of n. Is that right, everyone? That's really not different. If this is 4, year 4 will be 4. Year 5 going to be 5. Year 3 going to be 3. Always the same. Now we can generalize this formula. So let's use Pn to represent the output. This is the output. Now Pn equals this initial, this $1,000 is the initial value, is the deposit. It could be any number. We don't have to start with 1,000, right? So we call this P0. Just the initial value deposit. It can be any number. Now 1 represents the principal. You know that because say if you look at this one, if you multiply together, 1,000 times 1 is 1,000. 1,000 times 10%, that's the interest part, right? This one represents the principal. So it's part of the formula. Plus, how about interest rate? This interest rate is 10% compounded annually. That means this interest rate is for 1 year. This is how many years you have. What if our account is not compounded annually? What if the account is compounded monthly? That means they are going to calculate your interest at the end of every month. So you don't get whole 10% per month. You have to divide by 12 to see how much interest you get per month. And you also have to do it this many months, not this many years, because you have to do the calculation at the end of each month. That's why we need to change a little bit about this tool to correspond to the frequency the account is compounded. That's why they have this R over K. K represents how many times the account is compounded per year. Again, for example, if you have an account that is compounded monthly, so this whole yearly rate has to be divided by 12 to get a monthly rate. How much you get per month? I remember I mentioned that in the simple interest lecture, we mentioned that the interest rate and the time has to be consistent. I hope people still remember that. So if this compounded monthly, this monthly rate, the time has to be in terms of months. That's why they have this NK here. For example, if this K is 12, which represents 12 months in the year, N is time in years. Year, this many years times months, that's how many months. For example, if N equal to 5, you compound it monthly, 5 times 12 is 60. Is that true? If you do it every month, you do it 5 years, you're going to do it 60 times. That's why these two have to be multiplied together. So eventually, this is our compound interest formula, which calculate the total account value at the end in the future. And the area where people make mistake all the time is how to determine the K. K is how many times the account is compounded per year. So if you do it annually, you only do it once a year. If you do it monthly, you do it 12 times a year. If you do it quarterly, you do it 4 times a year because there are 4 quarters a year. You do it every quarter. If you do it with another frequencies such as semi-annually, semi means half. So if you do it every half year, you will do it twice a year. So in that case, K equals 2. Just make sure you get K correct. Now let's look at our first example. We deposit $1,000 at 10% annual rate for 3 years, compounded annually, find the total interest earned. This is exactly the same problem. Look at this one we used. This is the exact same problem. So we are going to do this using the formula so that you can see how I use this formula. And by the way, there's a reason we have this formula in the first place. Imagine our example is that we compounded annually for 3 years. What if we want to calculate this same account, but instead of doing it for 3 years, if we want to do it for 30 years? Do we still need to repeat that whole process here, year after year for 30 years? We do this repeating work for 30 times? That's kind of tedious, right? Even though in theory, yeah, we can do that, but it's tedious. Secondly, what if they change this compounding frequency from annually for 30 years to monthly for 30 years? That's 360 months. we do it every month, repeating work. We're going to have 360 of this. Certainly, we don't want to do it that way. That's why we have a formula. Once we have formula, no matter 3 years, 30 years, or monthly 30 years, the amount of work is the same, no difference. Okay, let's solve this one. Even though we are calculating interest, we have to calculate the total account value first, because this formula only gives us total account value. So Pn equals P0, 1000, 1 plus R is 10%. Since it's an annual rate, compounded annually, we only do it once a year, this is 1. And NK, we do it for 3 years, this N times K is 1. So actually this makes sense. Since you do it once a year, and this is just 1 plus 10%, and to the power of 3. Isn't this exactly the same? It's supposed to be the same, right? Because the K equal to 1. But let's do the calculation. 1 plus 10% is 1.1. 1 plus 0.1, 10% converted to decimal to the 3. Actually, we can add this together, 1.1, and then do the power of 3, but I keep it so that you can see we want to do this calculation in a consistent way, because later on you're going to have other numbers, and that will result in this part being a decimal with many digits. You don't want to write it down, because as soon as you write it down, you're going to have rounding errors, because it's countless digits. As soon as you write down some digits, you will have rounding errors. And that rounding error is going to compound itself. And after that, that bigger rounding error will be exaggerated by many times again. So how do we control the error then? That's why we don't do this division if you have K on the bottom. We let the calculator do the whole thing. So this equals, let's just illustrate this, demonstrate this, how to do that. 1000 times 1 plus 0.1 to the power of 3. 1331. And this is what we expected, right? Now, what is total interest? We know what to do. Total account value, subtract the original deposit, initial deposit, that's 331. That's way faster, right? Way faster. We get the same answer. But if you think about that, if we change to 3 years to 30 years, what's the difference? The only difference is that we change 3 to 30. It's still the same amount of work, no difference. So, okay, now I'm going to move on to do the second example. My goal is to make sense this formula, so to also help people to understand a little bit deeper about this compounding inner working. So let's look at this second example. We deposit $1,000 at 10% annual interest rate for 3 years, compounded monthly, find the total interest earned. So if you notice that the only difference between this one and the previous one is just one word. I changed from compounded annually to compounded monthly. Now we still calculate the total interest. The reason I want to do this is that the only factor that is different is compounding frequency. I want people to see the effect of this compounding frequency on your total account value. Okay, let's do that. Future value equals 1,000. 1 plus interest rate is 10%. Now our K, compounded monthly, K represent how many times you compound your account per year. Since you do it every month, you're going to do it 12 times a year. Now to the power of NK, N represents time in years, and same K times 12. So let's simplify this a little bit before we use calculator. 1 plus 0.1 over 12. You see, I don't do the calculation. I just rewrite this into decimal, and the calculator will do the whole thing. Now, let's make sense out of this before we do calculation. Since this is 10% is for the whole year, when you divide it by 12, you get 1/12 of it, 1/12 of it. That means this is interest rate for 1 month. And each 1 month, you get this much more money in terms of interest. And then you do it for 36 months. Hopefully this makes sense. And the interest rate and the time has to be consistent. This is how much you get for 1 month. That's how many months you have. Okay, now time to do the calculation. 1,000 times 1 plus 0.1 over 12 to the power of 36. We get $1,348.18. Usually we round it to the second decimal digits for the cents. Now the total interest. 1348.18 minus 1,000. That's $348.18. And if you recall, when we had the first example, the account is compounded annually. The total interest is $331. $331. This one $348. It's like about $17 more. So why we get a little bit more interest? Every number is the same, right? Only thing different is a compounding frequency. Now this account is compounded more frequently. We do the calculation of the interest at the end of every month. At the end of every month, we put the interest back to the principal so that the principal increase a little bit every month. So that every month you have higher principal to earn you more interest. You don't have to wait for the whole year for that original principal to increase. In other words, your interest you earned from the previous periods work for you to earn you more interest earlier because you compounded more frequently. That's the reason you get more money. Your money is working for you earlier than annually compounded account. Okay, move on. Let's look at the third one. This is exercise, but we do it as an example. We deposit $1,000 at 10% annual rate for 3 years. Again, everything is the same. Compounded quarterly. That's the only difference. So this time we need to find the total account value and the total interest. Now, if we think about that to see if this makes sense, and sure, we calculate the total account value first, but in terms of total interest earned, what can we expect? When we compound it quarterly, we have 4 quarters a year, right? We do it every quarter. So K equals 4 in this case. When K equals 1 compounded annually, we get $331 interest. When we compound it more often monthly, we get $348.18 interest. That's increase, right? Now we compounded quarterly 4 times. So 4 is between 1 and 12, right? So we can expect our interest earned will be more than $331, but less than $348 because it compounds less often than monthly. Let's see if that is true to make sense, right? So future value equals current value and times 1 plus interest rate. We compound it quarterly, so 4 quarters a year. And we do it 3 years, so we do it 4 times a year. Totally, we do it 12 times. So this equals 1,000, 1 plus 0.1 over 4 to the power of 12. And 1,000 times parentheses 1 plus 0.1 over 4 to the power of 12. So keep 2 decimal digits, 89 cents. So this total account value, total interest, 1344.89 minus 1,000 That's $344.89. This number is between 331 and 348. Again, it has to make sense. Okay, now let's look at the next one. Exercise problem. We do this as an example. So it's like an application problem, like a real problem. A certificate of deposit, we call it CD, is a savings instrument that many banks offer. It usually gives a higher interest rate, but we don't care about that. It's just a number for us. And suppose that you deposit $3,000 in the CD, paying 6% annual rate, but compounded monthly. How much will you have in the account after 20 years? Apparently, this is a compounding account because they mentioned compounding monthly, the frequency of compounding, and apparently also that we are looking for the future value. We are asked to find out the account value after 20 years, right? So after you realize this is a compounding account, write down that compounding account formula. So I'm going to do that. So this is the formula that we are going to use. We just need to put the right number in the right place. When you do this, all of this finance homework problem, it is critical for you to identify what kind of account you have. You could have simple interest account, you could have compounding interest account, you could have annuity account, right? Different account have different formulas to use. That's why you need to identify what kind of problem you have first. This one is compound interest account, so we use this formula. We're looking for the future value. In other words, all of the other numbers have to be given. You just need to identify which one is which. And besides, let me mention this is the right moment to do that. For this simple interest account, they can only ask you two questions. One is that the future value in the question. They ask you for the future value. Another type of question is that they ask you for the current value, how much you have to deposit in order to get the future value. And later on, we are going to have an example to address this kind of problem where you need to find the deposit amount. But for now, let's solve this. So future value equals deposit $3,000, 1 plus interest rate, which is 6. This interest rate is always annual rate. Now we compound monthly, certainly this is 12. And to the power of nk, we have 20 years. Each year we do it 12 times, so totally we compound it 240 times. That's why controlling error is very important. If this part has running error, this whole thing going to be compounded 240 times. That error going to be compounded 240 times. And that error also going to be exaggerated by another 3,000 times. So that's a terrible result. And in your homework assignment, from my memory, they only tolerate plus minus 5 cents. So your answer has to be within 5 cents above and below of the true answer to be considered correct by the computer. That's why we need to control the rounding error so that we don't do this part individually, separately. We let calculator do the whole thing. So 3,000, 1 plus 0.06, convert percent to decimal, over 12 to the power of 240. Let's see what we get. 3,000 times parentheses 1 plus 0.06 over 12 to the power of 240. Yeah, looks good. So we got $9,930.61. So that's the answer to the question, the future value. $3,000 becomes almost 10,000 after like 20 years, given these terms in this account. Now another exercise problem, and there's really no fundamental difference. Only difference is that we have compounding frequency, which is semi-annually. So we do this as an example just for the purpose to make sure people understand that compounding semi-annually means k equals 2. It's not 6. Semi means half. Semi-annually means every half year. If you compound your account every half year, you can only do it twice in a given year. So k equals 2. So what is the question? Amount of interest round to the cents. So let's do the account value first because this formula only calculates the account value first. This is compounding account. We deposit $1,000. We get 8%, but compounded semi-annually. And we have 12 years times 2. Totally, we do it 24 times because we do it twice a year. So 1,000 times 1 plus 0.08 over 2 to the power of 24. 1,000 times parentheses 1 plus 0.08 over 2 to the power of 24. So everything is good. We get $2,563.30. So more than double. And we are looking for the interest. So we have to have another step. So this is total account value so far. And minus original deposit. So the interest amount is $1,563.30. So I only rounded when we have final result. That means no matter how big the number we work with, our error is always within 1 cent. So no more than 1 cent error. Now, this is the second type of problem for the compounding account. They call it present value of a compound interest account. In this case, we are looking for this P0. Again, they can only ask you 2 questions. Either they ask you for the future value given the current value, or they give you the future value to ask you to solve for the current deposit amount. They don't ask anything in here, how to find this, because that part requires higher mathematics skills. We don't do that in this course. Okay, scenario. Let's mention this like real life scenario so that you know actually this is practical, this makes sense in real life. Imagine this, actually we can read this one to explain the scenario. This is perfectly fine. Let's look at that. It says you know that you will need 40,000 for your child's education in 18 years, like a newborn baby. If your account earns 4% compounded quarterly, how much would you need to deposit now to reach your goal? So this is like a real thing. You have a newborn, you know you're going to send that person to college in about 18 years. So you have 18 years of time. And this 4% compounded quarterly is like a term in the financial product in the bank account. You can always get this kind of information from a banker or from a financial advisor, all of those. So you can get that kind of information easily. Now you know you need or you plan to have 40,000 in 18 years when that person is ready to go to college. That's a future value, right? So everything is good in theory, but there's only one catch, one problem. You have to know how much you have to deposit today in order for this whole thing to happen. If you say after a calculation, you say, oh, I don't have this money to deposit today, nothing gonna happen, right? So we need to know how much we're supposed to deposit today under these terms so that after 18 years, we have almost exactly $40,000. Okay, let's do that. First, we realize this compounding account, and we also realize this number given is future value, and we're looking for the current value, deposit amount. So in other words, in this formula, we're solving for P0. So we just plug in numbers, future value is 40,000. After we understand what kind of problem we have, calculation part actually is the easy part. So equal to P0 times 1 plus interest rate, 4%, compounded quarterly, that means we do it 4 times a year. And K represents how many times the account is compounded per year. and we have 18 years, and each year we do it 4 times. Totally, it will be compounded 72 times. So let's say 40,000 equals P0. This is going to be 1 plus 0.04 over 4 to the power of 72. Now, I'm going to do this in one step. If you prefer to do this separately, that's totally fine. Just keep this in mind. You need to control error because you prefer to do this separately. That means that's the middle step. It's not the last number where you do rounding. So to control the error, you want to take at least 6 to 8 decimal digits. In that case, if you use 6 to 8 decimal digits, you can handle up to $1 million range without big error, rounding error. That means you will have error, but your error is in terms of cents, not in terms of dollars. But I'm going to do this in one step so that there's no error. P0 equals 40,000. Remember, if you do the calculation, this will be one number in the end. We just don't know what it is for now, but it will be one number so that I just divide by this number on both sides to get P0. So 1 plus 0.04 over 4 to the power of 72. That's all we need to do using calculator. So 40,000. That's right. Now, since we are looking for the current value, we expect that number is smaller than future value because future value has interest in it. It will be higher. So in other words, if we get a number bigger than 40,000, something really, really wrong. So 40,000 divided by parentheses 1 plus 0.04 over 4, close the parentheses, to the power of 72. Okay. We get $19,539.84. That's present value. That's P0. It's a little bit more less than 20,000. That means over 18 years of time, you saved about half amount of money. Save a little bit more than 20,000. Time is money. Now exercise. So let's see how many questions we have. So we have totally 3 more questions. Let's work them out one by one. First, find the present value. It's also called principal. Round to the nearest cents. So future value, how many years we have, interest rate, annual rate, how often the account is compounded. So this is a very simple one. We just found P0, right? Future value equals P0 and 1 plus interest rate divided by K. Annually, K will be 1. And NK, N represent times in years times 1. So this is a straightforward one. 7,300 equals P0, 1 plus 0.05. You don't need to divide by 1 because it won't make any difference. So P0 equals 7,300 divided by 1 plus 0.05 to the power of 4. Again, the result should be smaller than this number. 7,300 and divided by parentheses 1 plus 0.05 to the power of 4. Yeah, everything is right. So we get $6,005.73. Again, a little bit smaller than that, about $1,000, more than $1,000 small, almost 1,300. Okay, now next one, same question, we need to find the present value. So we just have a different set of terms. So we just redo the calculation. Future value equals P0 times 1 plus interest rate. We compound it quarterly, that means we do it 4 times a year, to the power of NK. 4 times 4, totally we do it 16 times. 4,200 equals P0, 1 plus 0.06 over 4 to the power of 16. P0 equals 4,200 divided by this whole thing. 1 plus 0.06 over 4 to the power of 16. Okay, now 4200 divided by parentheses 1 plus 0.06 over 4, double check, to the power of 16. Yep. $3,309.73. That's how much you have to deposit today, so that after 4 years, the account is compounded 6% annually, 6% at 6% annual rate, but compounded quarterly. After 4 years, you will have 4,200. The next one going to be the last one for this video. And Brad wants to have 17. It's like an application problem. Brad wants to have 17,000 available to buy a car in 5 years. That means future value, 17,000 in 5 years. How much must he deposit now at 9% compounded monthly to reach that goal? So we don't really care too much about this. It's just terms. The main information from here is that we are given future value he needed. We need to figure out how much he has to deposit today under the current terms to get that 17,000. In other words, it's the present value of a compounding account problem. So future value equals present value times 1 plus R over K. K compounded monthly, that's 12, to the power of NK. We have 5 years. We do it every month, so we do it 60 times. 17,000 equals P0, 1 plus 0.09 over 12 to the power of 60. See, exactly same calculation. 17,000, 1 plus 0.09 over 12 to the power of 60. 17,000 divided by, before we do the calculation, let's say this time we get higher interest rate. You notice that we have monthly compounding, which means compounded relatively often, and time is money. I keep saying that, right? That means this time we expect that your principal going to be a little bit lower relative to the total account value in the future, because when you have longer time, when you compound it more often, you earn more interest. In other words, in your total account value in the future, interest getting a bigger portion of it. If your time getting longer, your interest rate getting higher and higher. So divided by parentheses 1 plus 0.09 over 12 to the power of 60. Oh. To the power of 60. Yeah, that's right. So we get $10,857.89. So from 10,000 to 17,000, almost a little bit over 6,000, and the interest amount earned a little bit over 6,000 actually, divided by 10,000, 6 out of 10, you earn about 60% interest actually on the original deposit amount. And that's it. That's the whole thing basically. See you guys in the next video.